Thank you. Hi, everyone. Thanks for coming. So today we will talk about the identification of communities in network. And more specifically, I will present an algorithm that can handle the overlapping communities. The algorithm I will talk about is a particular example of a spectral algorithm, which is a family of algorithms that has been successfully used until then to detect non-overlapping communities. So first, what is a community? So the problem in the community detection literature is that there is no clear definition for a community, but we will think of it as a group of nodes in a network that are more connected within themselves than with the rest of the network. And this is the case, for example, if you look at a political blog networks in which there is a link between two blogs if one has a links to the others. And so the size of the nodes is, well, I don't remember, but thanks to a clustering algorithm, this graph was partitioned in two communities, which actually corresponds to Democrat and Republican. So in that case, a node, a blog, will not belong to two communities. You are either Democrat or Republican. But in other example, it might be relevant to consider overlapping communities. So this is the case, for example, in an ego network. So an ego network is you take a social network, you choose a central node, and you form the graph of all the friends of this node, and you remove the central nodes. And if you do so, you realize that so you can identify some communities like friends, colleagues, I don't know, member of some sports team, and sometimes people will know each other, and it is relevant to view some of the nodes as being part of two or more communities. This is also the case if you look, this might be a toy example, as co-authorship networks. So you build a graph where nodes are authors. You draw an edge between them if they published a paper together. And you choose as communities the conference to which they published. So here I isolated two conferences corresponding to two different areas, so NIPS for machine learning and Sigmetrics for networks. And you see that these two people published paper in both conferences. And here I draw a link because we submitted a paper somewhere together. But yeah, for example, me, I'm a pure node from machine learning for the moment. So this is maybe a toy example, but in other real-world networks, for example, I can mention something from biological network called protein-protein interaction networks. When by observing interaction between protein, you try to identify protein complexes that correspond to some biological function. So this is used for this purpose by biologists. So in this talk, I will rely a lot on random graph models. So why? So the idea is to assume that the network that you observe and in which you want to find overlapping communities, you can assume that it is drawn from some random graph model that actually relies on some hidden communities. And this assumption can inspire some algorithm to do community detection that are therefore called model-based methods. So in other words, you see the community detection problem as some estimation problem in some random graph model. So for example, you could use tools from statistics like maximum likelihood or things like that, which is not what we are going to do. But so the model can inspire some algorithm. It can also be used for evaluation purpose because you can evaluate any method, model-based or not, on a network that is sampled from a random graph model. And it also, to justify that an algorithm is good, a possibility is to prove that it actually recovers the communities that were hidden in the random graph model. So this is consistency results, and we are going to prove such result for the algorithm I'm going to show you. So the outline of the talk will be as follows. First, I will review what happens in the non-overlapping case. Especially, I will introduce an important random graph model called the Stochastic Block-Model and explain, using this model, what the spectral algorithms are. And then I will extend this model to the stochastic block model with overlaps and present the estimation problem that we are looking at, so with overlapping communities, and then the way we solve it with an estimation procedure. And then I will provide consistency results for the proposed algorithm, as well as an evaluation on simulated and real-world networks. So, what is the stochastic block model? So first, I will talk a lot, as I told you, about random graph models. So my graph in this talk will be undirected, unweighted, so you can associate to them a matrix, an adjacency matrix containing a 0 and 1. And in our random graph model, we will assume that this symmetric matrix is drawn, that each entry is drawn according to some Bernoulli distribution with mean Aij, which is the corresponding entry in what is called the expected adjacency matrix. And of course, we will work with expected adjacency matrix that do depend on communities. Like here in the stochastic block model, that depends on a number k of communities, mapping from nodes to communities, telling which node is in which community, and some connectivity matrix B of size k by k. And so the entry Aij of the expected adjacency matrix, so the probability that the node I and j are connected, will be of the following form. So you see that it depends only on the community of node I and the community of node j. And I just mentioned that it can be rewritten in the following form if I introduce a membership matrix Z, which is of size n times k. And in fact, each line is going to have exactly 1, 1 that indicates what is the community of this node. So the stochastic block model can be, so here is an example. So the simplest example often studied in papers. So you have two communities. So the node in red from one community, the node in blue from another community. And the probability, the connectivity matrix is as follows. So that the intra connectivity probability is P, and the extra connectivity probability is Q, which is traditionally very smaller than P. So the SBM can be used to explain and to motivate, in some sense, the spectral algorithm. So if we look at the form of the adjacency matrix, a first simple observation is the fact that two nodes that are in the same community are going to have the same line in the adjacency matrix. So more specifically, we have this following equivalence. So if you give me the expected adjacency matrix, I just look at the lines to group the nodes in communities. Now, if you give me only an observed adjacency matrix drawn from the random graph model, it's not very likely that two rows in the same community will be similar. You will observe 0 and 1, but they won't be on the same place. So you cannot just use this on the expected adjacency matrix. But the idea is to use it on a different matrix built using the eigenvector of matrix A. Indeed, it is possible to show, and I will explain you a bit later on the other model, that if you take the matrix U of the k eigenvalues of A with largest, eigenvector associated to the largest eigenvalue, the same property still holds. Which means that if you look at the matrix of k largest eigenvector of A, do the same, look at the rows and group the nodes that have the same row. But so now this matrix U is no longer a binary matrix, I mean the empirical version. So there is some hope that these things will work also with the matrix of eigenvectors associated to the observed networks. And this is actually the idea behind the spectral method. So now we work, I told you, with the matrix A hat of the adjacency matrix of the observed network. So the first step of a spectral algorithm is to is called the spectral embedding. So the computation of this matrix U hat of eigenvectors associated to the largest eigenvalues. So why it is called an embedding? Because now to each node you can associate a vector in Rk, which is going to be the associated line in the matrix n by k of eigenvectors. And now, so if there was not this hat notation, you would just group the node according to their rows, so according to their representative. And here you do this approximately, so that is, you are going to perform clustering in Rk of these things. So this is a spectral algorithm. First, spectral embedding, because this matrix uses the eigenvectors of the matrix, and then a clustering phase to recover the communities. So there are many other spectral algorithms that are either based on a different spectral embedding, that is either than looking at the eigenvector of the adjacency matrix, you may look at the eigenvector, for example, of the Laplacian, or in some method you can replace the k-mean clustering by something else. And also there are other possible ways of motivated spectral algorithm. Here I did so by showing that because of the geometry of the adjacency matrix, it is quite natural to try to do this. But you can also see some spectral method as a convex relaxation of some complicated optimization problem over all the partition on the graph. So it is one way of motivating things. So now let's move to the overlapping case. So I'm going to introduce a model called Stochastic Block-Model with overlaps, so that appeared to us as the simplest possible generalization of the SBM. Look here, the expected adjacency matrix has exactly the same form. So depending on a number of communities K, a connectivity matrix B, and a membership matrix Z. But this time, the membership matrix will be any matrix in 0, 1 to the n times k. So in other words, we don't force each row to have only 1, 1. But now the ith row of matrix Z, that we will often denote by just Zi, will be an indicator vector indicating the different communities to which each node belongs. And our goal will be to perform estimation of the parameter Z, which is a matrix, but also on the number of communities, which is in general unknown. So we will build some estimation of K that we denote by K hat, and some estimation of Z that we denote by Z hat. Of course, the estimation of Z needs only to be accurate up to a permutation of the rows, because it would corresponding just to a relabeling of the communities. So I just present you two performance metrics that we consider for this estimation problem. So for example, we may look at the number of misclassified nodes of our estimator, which is actually the number of nodes for which we made at least one error in estimating the corresponding membership vector. So the membership vector is the row of a given node in this membership matrix. We can also look at the estimation error, which is the fraction of entries in the matrix Z that were not correctly recovered. And of course, if our estimate K of the community is wrong, if we don't recover the right number of communities, then the error is maximal and the number of misclassified nodes is considered to be equal to all the nodes of the networks. So is it possible to perform estimation in any SBMO model? So the answer is sadly no, because to do it, we need the model to be identifiable in the following sense. So if our expected adjacency matrix can be written in two different, so if there exists two possible decompositions for the expected adjacency matrix, of course we cannot come up with an estimate that would choose between Z and Z prime. So a necessary condition to perform estimation is that if we have this, then Z and Z prime are equal up to a permutation of the rows. So here I give some 3 different potential SBMOs, so by giving the matrix B and the matrix Z, for which actually we come up with the same model, so the same expected adjacency matrix. So you can see that the second one is a particular case of the SBMO. It is an SBM because it has only pure nodes that belong to a single communities, and we could not discriminate, for example, between the two. So we will need to add some assumption on the matrix B and Z to have an identifiable model. And we see from this example that the assumption won't be that there is at least two communities per node, because here we have also 2 examples in which we have at least 2 community per nodes, but we don't have the same. Here we have K community. Here we have 3 communities. So the simplest conditions that we came up with are the following. So if we assume that the matrix B is invertible and that each community contains at least a pure node, so in the following sense. So for each K, we will need to have 1 node that belongs only to this community. And you see that this is not the case in this example, because there is no node belonging to either of the communities. So from now on, we will assume that these assumptions are satisfied. So now let's think about how to estimate the matrix D. So the first idea is to remark that actually SBMO is just can be viewed as a particular case of stochastic block model by adding communities. So in this SBM, there will be up to 2 to the K community corresponding to all the possible mixtures of communities that are present in the network. So the Z for which there exists a node having this membership vector will form what we call the subcommunities. And so the corresponding connectivity matrix of this SBM with more community will be the following. So here I show you on an example. We have, say, an SBMO with 3 overlapping communities. And for example, a node here in the intersection of C1 and C2 will have a membership vector 1, 1, 0. And we see that we could look at this part of being a community indexed by 110. So the same is true for the rest. So as I explain you I show you some method to perform community detection in the SBM, so recovering all this community. A first idea would be to build an algorithm that, as a first step, would reconstruct all the subcommunity and then try to do something to come up with overlapping underlying communities. But this is actually not quite a good idea, because first here we have much more communities, and the performance of community detection deteriorates a lot in practice when there are a lot of communities. And even if we had accurately found all the subcommunities, then to find the overlapping community, we have to consider all the possible combination of subcommunity, and this is really computationally intensive. So our approach will try to directly estimate the overlapping communities. And to do so, just like what I showed you with the SBM, we are going to look at the structure of the spectrum of the adjacency matrix. So if we assume that our SBMO is identifiable, we know that, so this is the adjacency matrix in any SBMO, and we know in particular that the membership matrix must belong to this set Z of matrix that have 1 pure node per community. So we know that for Z. And because B is invertible, we also know that A is going to be of rank K. Now, if we look at the same matrix as before, so the matrix U whose columns are K are the k normalized eigenvector associated to the k non-zero eigenvalue of A. So A is of rank k, so it has exactly k non-zero eigenvalue. So actually, this vector u1 up to uk, they form a basis of the image of A. And because of this writing, you can see that the image of A is included in the image of Z. And therefore, there will exist some matrix X of size k by k, such as U is written U can be written as Z multiplied by X. And this is the key decomposition that we will use to recover the matrix Z. And actually, if there is a decomposition of U of this form, we can prove that the Z prime must be equal to Z up to a permutation. So this was already used in the proof of identifiability. And it is actually quite simple to prove. So in fact, any decomposition of this form will make appear the matrix Z, which is of interest. And this motivates the following estimation procedures. So we don't have access to the matrix U. So as before, we will take its empirical version, so the matrix of leading eigenvector of the observed adjacency matrix. And we are going to find the closest possible decomposition of the form Z multiplied by X in a Frobenius norm. So here I recall what the Frobenius norm of a matrix is. It's simply the sum of all the square terms, or for example, the sum of norms of its line or columns. So this is the estimation procedure. So this gives you Z hat, provided that it is actually numerically possible to compute an answer. And because actually this matrix Z with all with the constraint of all the pure nodes is quite a complicated set. And in practice, what we are going to solve with our algorithm that we call combinatorial spectral clustering will be a relaxed version of this optimization problem, in which here we will just minimize over all the matrices containing 0 and 1 that have always non-zero lines. So this is the algorithm I'm going to discuss about later. And I told you that we also want to estimate K, the number of communities. And so the estimate of K that we suggest is to take the number of eigenvalue of the adjacency matrix that are larger than this threshold. Here you see that what appears here so Dmax hat is the empirical maximal degree that is observed in the graph. So this thing can be computed just by looking at the graph. So it is really an adaptive way of choosing which eigenvectors to keep in the algorithm if you don't know K. So what I'm going to do first is to explain you why this procedure is working. So to give a kind of theoretical analysis of the estimation procedure I just introduced. So our goal is to find conditions for this optimization, so the Z prime computed in this way to be an accurate estimate of Z in the sense of our misclassified nodes or of the number of errors in the matrix. So for analysis purpose, we will actually analyze only a slight variant of this procedure in which the set Z of all matrices which have exactly at least one node per community is replaced by this set Z epsilon, in which in fact it is the set of all matrices for which the proportion of pure node for each community is larger than epsilon. So statistically, it makes sense because if you have only one pure node and the network is going to be very large, it's very unlikely that you don't make a mistake on any of these pure nodes. And so the epsilon will be chosen to be smaller than the smallest proportion of pure nodes in the limit. So our analysis will be for growing networks. And so that's why I now introduce some scaling that we are going to look at. So we are going to analyze the solution of the problem P epsilon in an SBMO whose adjacency matrix is of this form, where we introduce a parameter alpha n called a degree parameter, and where now B is assumed to be independent on n. And of course, as Z is dependent of n just by its size, we cannot say it is independent of n, but we will make some assumption also on Z. So why is it called a degree parameter? Because if you look at the degree of node I, which is the number of the average number of neighbors of this node, so this is the expected degree, you can see that it is written on the following way. So it is proportional to the parameter alpha n, and it is multiplied by this quantity. And actually, the assumption we make on Z is that when n goes to infinity, this quantity also tends to some constant. So when n grows large, the degree is really governed by the parameter alpha n. So we also introduce something important, which is the overlap matrix. So we assume that if we compute this quantity, so 1 over n multiplied by Z transpose Z, it tends, when n goes to infinity, to some matrix. And why is it called the overlap matrix? Because if you look at the term KL of this matrix, actually you realize that it is just the proportion of nodes that belongs to the community K and to the community L. So in the sequel, and to simplify the notation, I will just assume that actually O is equal to this thing. So I wanted to have an O that does not depend on n, and because of this assumption, the overlap matrix don't depend on n when n grows large. So the point of introducing this overlap matrix is that it helps us characterizing the spectrum of A in terms of the spectrum of matrix that do not depend on n. Indeed, it can be shown that if we take an eigenvector of so some matrix M0 that is constructed based on the overlap matrix and on the membership matrix that do not depend on n, then U equal Z O to the minus 1/2 x is an eigenvector associated to not the same eigenvalue, but to the same eigenvalue multiplied by alpha n. So to compute eigenvectors of the matrix A, you look at them of the form U multiplied by something, and you see that the something is also the eigenvector of a smaller matrix. So the point of this result is that first it is going to help us have a nice form for the matrix U, but also we see that the non-zero eigenvalue of A will be of order big O of alpha n when n grows large. So to analyze our estimation procedure, a first thing to understand is why is the spectrum of U hat close to the spectrum of U. And this result also helps us understanding that. So why is this? Because so what we know from this result is that the spectrum of A is the following. So there will be, of course, a lot of so the eigenvalue 0 will have a large multiplicity because A is only of rank K. And the K non-zero eigenvalue of A will be alpha n mu1 up to alpha n mu k, where mu1 up to mu k are the K eigenvalues of the small matrix that does not depend on n. So now if we have the spectrum of R hat, so R hat can be seen as the expected adjacency matrix plus some perturbation. And actually, it is possible to show using matrix concentration results that the spectrum of the perturbation will always lie within square root of 2 multiplied by the maximal degrees, the same here. So we know that the perturbation has a bounded spectrum, and if the spectrum of A is sufficiently far from this threshold, so the maximal eigenvalue of the noise, then we can show that the spectrum of the eigenvalues of A hat will not be too far from the eigenvalue of A. And then using some extra tools from algebra, so knowing that these eigenvalues are separated from the rest, so using what is called the Davis-Cahan theorem in algebra, you can go from the closeness of eigenvalues to the closeness of eigenvectors, which is non-trivial to analyze in general. So using these two tools, so concentration results and deterministic stuff from algebra, we were able to show the following result. So the result bounds the deviation of U hat with respect to U in Frobenius norm. And what is featured here is so Dmax, the maximal expected degree in the network, and lambda mean of A, which is the smallest non-zero eigenvalue of A. And so more precisely, we see that here we give an adaptive result in the sense that we give a way to choose an estimate of K, which will be the number of eigenvalue of A largest than this threshold. So if K hat is chosen in the following way, if U hat is the matrix that contains, again, the leading eigenvalue of A, then provided that the maximal degrees in the graph is large enough, so larger than something like log n, then we have that K hat is actually equal to the rank of A, which is K in our SBMO example, because this result holds for any random graph model. And so we have this bound. So in the particular case of the SBMO, I already told you about this degree parameter, and so the fact that the Dmax will be of order alpha n. We looked closely at the spectrum of A as well, and the smallest eigenvalue of A, which is non-negative, will be of the following form, where mu0 here would be the smallest non-zero eigenvalue of the matrix M0. So this tells you that the ratio here in a range is of order 1 divided by alpha n. And for this result to show that the estimate is good, we will need, therefore, then that alpha n divided by log n goes to infinity. And we will see that with this condition, we will be able to show that the algorithm recovers the community. But to prove, to give a consistency result, so an analysis of the estimation procedure, there is another important step, which is the sensitivity to noise of the decomposition U equal ZX. So because of the result on the spectrum of A, I told you it permits to give an elegant decomposition for U. So we know that U is written in the following with this matrix X. But what we are doing in the estimation procedure is that, so we have, we look for an approximation of U of the form Z hat multiplied by X hat. And so we need to show that if U is well approximated, then the corresponding decomposition should be close to this one. And so this result tells us what we need. So it tells us that if we have Z prime and X prime, such that the decomposition Z prime, X prime is very close to U, in the sense that on some set, for all nodes in some set N, we have this. So this tells you that it is not equal, like in the previous proposition, but it is not far from being equal, so you allow some noise. If this is the case, and if there exists in the set of nodes considered nodes I1 up to Ik and J1 up to Jk that are pure nodes in the matrix X and in the matrix Z and Z prime, then there exists a permutation matrix such that the true Z is only a permutation of the row of the matrix Z prime for the nodes on the set N. So this is the key result that we also use in the proof. And here, in fact, the authorized level of noise is governed by some parameter D0, which, because of this result, can be seen as the smallest distance between rows of the matrix X or between linear sums of rows of the matrix Z. So with these two ingredients, let me show you the final result that we obtained for the adaptive estimation, adaptive solution of P epsilon. That is the solution in which we let K hat be the estimator that I mentioned before. So what we proved is that if alpha n divided by log n tends to infinity, so if the graph is sufficiently dense, but still sparse, because we don't need alpha n to be of order n to some power. Log n is still relatively small compared to n. Then with high probability, we upper bound the number of misclassified node for the estimator Z hat by something of the form log n divided by alpha n. And here we recover the two constants that I introduced before and that are related to these small matrices that govern the spectrum of A. Okay, so we showed that something very close to the original optimization problem P is consistent. So because when n goes to infinity, this is going to go to 0 almost surely. So now something I didn't mention yet is that it is not necessarily so easy to solve the optimization problem that I'm talking about. And so the practical implementation that we develop, we call it combinatorial spectral clustering because it is really reminiscent to the spectral clustering algorithm I mentioned before. Why? Because the first step is again a spectral embedding. So we compute this matrix U hat of leading eigenvector of the empirical matrix. And then the second step is a kind of clever clustering algorithm that is going to recover overlapping communities. And we are going to solve the problem P prime by using alternate minimization, because so the Frobenius norm of Z prime X prime minus U hat can be written in the following way. And you see that if X prime is fixed, to minimize this, for each node I, we are just looking at the Z prime I, which minimize this argument. And it will also possible when to solve the other way around, that is, when the Z prime are fixed, find the right X. So this is summarized in the following implementation of the algorithm. So we see here that it also depends on some upper bound on the maximum overlap that we may have. And if we don't have it, we just let it to K. So it may happen that we know that we want to find communities that only overlap 2 by 2, or that a node can belong to a maximal number of community, and this could speed up things in practice. So also, the algorithm will be quite sensitive to initialization. Because any alternate minimization, so for an alternate minimization algorithm, we know that we are going to converge in a fixed number of steps, because each time we diminish the objective to a local minimum of this objective function. But what we are looking for is the global minimum, and so we have to be careful on where we initialize our Z, our Z, and X. And here we propose to do so with what is called a K-min plus procedure. So given the the matrix at U, we are going to choose carefully k rows of U to initialize the algorithm, and k-means plus plus permits us to choose these initial rows as far as possible from each other, and there is also some randomization. And so we alternate between these two steps. So I explained you already the maximization in Z when X is fixed. So for each node, we are just going to choose this Z. So this can be computationally intensive because it could be over 2 to the k possibilities. And then the optimization in X has also a closed form, which can be shown to be the following. And in case the matrix Z hat obtained on previous step is not invertible, we just rationalize the algorithm, because we want this matrix to be invertible, because in the end we know that the solution will have one pure node per communities, and if it's not invertible, then it has not. So we are anyway in a bad part of the space. So this is the algorithm, and now I show you how it performs on simulated data first. So I'm going to compare combinatorial spectral clustering to two other spectral algorithms. So the first is the usual spectral clustering I told you about. Except that we normalize the rows, because in practice it is not to work well if there are some heterogeneous degree. But anyway, the first algorithm, CS, is an algorithm which is designed to identify non-overlapping communities. So it is expected to perform quite bad. But the second algorithm is another spectral method that was very recently proposed and that we call the OCAM. In fact, it is another spectral algorithm, so based on a different spectral embedding and a different clustering phase that is designed to fit a different random graph model that depends on overlapping communities. So we did some experiment on network with 500 nodes and K community, letting a quite large scaling degree parameter. So because our algorithm is supposed to perform well only if the degrees are large enough. So if this parameter alpha n is larger than log n, we choose some diagonal connectivity matrix, and we choose a membership matrix Z by imposing some maximal overlap. So here we will consider that one node belongs maximum to 3 communities, and we vary the fraction of pure nodes that are present in the network. And we see that, so if P is equal to 1, it means that all the nodes are pure, so there is absolutely no overlap. And when P goes to 0, there is more and more overlap. So when P equals 0, all the nodes belong to strictly more than one community. And we see that, so the error of the 3 algorithms, so spectral clustering has the smallest error, especially when the overlaps grows large. And what is expected, so spectral clustering perform quite bad, except when the overlap is small. And to be more fair, we also simulated some data from the other random graph model, so OCAM, which was motivated by the other algorithm. And so sometimes, of course, the OCAM algorithm performs well because it is designed to fit this model, but at the same time, the difference with our algorithm is quite narrow. So then we tried some experiments on real-world networks, so including first the ego networks that I talked about in the introduction. So there is a data set available on SNAP, which is a group at Stanford who have a lot of network database. So actually, I used some pre-processing on the network that I don't describe here, but to make sure that there are sufficiently pure nodes in each of the communities that we kept. And finally, so there were 10 Facebook network in the original database, so we were able to keep only 6 of them after the preprocessing, and we wanted to keep only those who had a significant overlap. So we only kept the one for which at least 1% of the node belonged to more than one community. And so it gives us the following result for the 3 algorithms. So here are the characteristics of the networks. So number of nodes, number of community. C is the average number of community per node. So it indicates the level of overlap of the network. And if we see that on average we have a small overlap on this network. And here we have the error of the 3 algorithms, so as defined before. And I also report the false positive and false negative, so the number of nodes for which we had 1 in the estimate, whereas it was 0 in the other, and the converse. And we see that so combinatorial spectral clustering perform a little bit more, but so here is a standard deviation which is quite large, so it was not, but it is the same order of Occam. Sorry. But what we noticed also is that the improvement over spectral clustering, the one that is not designed for overlapping community, is quite small. So these networks were not really adapted for overlapping community detection. So we found we tried to build our own networks with more overlap by constructing some co-authorship networks using the DBLP database. And so we chose here as a ground truth community 3 different machine learning conference or group on conference. So we took the nodes to be all authors in one of these conferences. We draw edges if they co-published. It gives us some quite large networks. And on this, so here the overlap is quite large. And we see that compared to the other experiments, combinatorial spectral clustering really outperforms its 2 competitors, but the overall error is, however, still quite large in the 2 cases. And especially the level of overlap is clearly underestimated. So one possibility is that here, if we look at the mean degrees in these networks, they are really small. So it is known that it is more complicated to do community detection in sparse network. And we try to investigate a little bit this phenomenon on simulated data. So we took a very simple SBMO with 2 community, a diagonal connectivity matrix, such that here there is we fix a fraction of pure nodes. So there are SN nodes that belong only to community 1, SN nodes that belong only to community 2, and the others that belong to the two communities. And so we proved that the algorithm works when alpha n is much larger than log n. And here we set alpha n equal 1, which corresponds to a sparse case. And so we tried combinatorial spectral clustering for different values of S. So again, by varying the amount of overlap present in the network. We also try it for different values of A. That gives a different curve at each time. And we see that when the amount of overlap, so S is not the amount of overlap, it's the fraction of pure nodes. When the fraction of pure nodes goes below some thresholds, it seems that the algorithm is not working anymore. And actually, this could be explained by looking a little bit more at the spectrum of matrix A. Actually, in this simple 2 community case, it is possible to compute by hand the non-zero eigenvector. And specifically, we show, so when alpha n is equal to 1, that there are 2 non-zero eigenvalues, which are A multiplied by 2 minus 3S and SA. So this one is larger than the other. We computed the associated eigenvector so that we can have an idea of the behavior of an algorithm. Because so nodes in community 1 will be mapped in the spectral embedding to the vector 1, -1. Nodes in community 2 will be mapped to the vector 1, 1. And node in the overlap will be mapped to 2, 0. And you see that this one is the sum of the two others. So what happens? The problem may come from the noise that there is in the sparse case. In fact, what can be shown is that the eigenvector of, actually here I put the adjacency matrix, but in fact it is some more complicated matrix that should be used in this sparse case, but I put it under the carpet. You can ask Marc if you want some details. Anyways, this matrix is such that the eigenvector due to the noise will be smaller than square root of this quantity. So what could happen is that from these two eigenvectors, it may happen that the first is out of the bulk, so out of the eigenvectors due to noise, whereas the second eigenvector is mistaken with noise. And this happens if SA is smaller than this threshold, which is equivalent to this threshold. So we conjecture that if the parameter S and A satisfy this inequality, it might not be possible to classify the pure node correctly. And so I tried to add the theoretical threshold on the plot. So maybe it should be a little bit more right, I don't know. But anyway, at this point, the algorithm appears not to be working anymore. So yeah, that's it. So I show you an algorithm, so a new spectral method designed to find overlapping communities. So I proved its consistency and show its performance on real and simulated data. And there are plenty of questions raised by this work. So one might be to explore a bit further this phase transition, which has been done a lot for non-overlapping community detection. Then there is the algorithmic issue of the problem P prime. We could come up with some heuristic to simplify the algorithm. And then other questions are, so here we show, we presented a spectral embedding based on the adjacency matrix. And actually we tried with the Laplacian, but we didn't find a structure that could be used like the one we had for the adjacency matrix. So it is another possible direction of research. And also this algorithm relies a lot on the fact, so which was in our identifiability condition, that there must be one pure node in each community at least, and even a fraction of pure nodes. But if we want to do like some hierarchical community and something like that, this assumption does not make sense. So another direction is to maybe find other identifiability conditions that do not require this assumption. Thank you for your attention.
Is there any question? What about when you compare the running times between CSC and SC and OCAM?
So in terms of running time, of course, combinatorial spectral clustering will be more complicated than spectral clustering, because what I didn't mention is that actually in this step, if you take the classic spectral clustering, this is replaced by what is called the k-means objective, and k-mean is exactly the same optimization problem, but here you restrict yourself to matrix having only a 1. So it will be, of course, more costly. And compared to OCAM, in fact, OCAM requires to do k-median clustering, which requires, so you optimize you remove, it is the sum of the norm, but without the square. So to optimize it, you have to do a gradient descent, and it is quite heavy to implement. So on my computer, OCAM is smaller, but maybe the author of OCAM were more clever in implementing the algorithm. So I don't want to
But there is a gap between this with the algorithms designed for overlap and just taking SC. So like the original spectral clustering is much faster, or I don't know.
Yeah, it's really much faster, but at the same time, it does not the same thing. It outputs a partition, and we want, but yeah.
But both have this, like, both Occam and CSC are more or less in the same.
Yeah, more or less in the same.
It's a question which is linked to. I was thinking of incarnation of that in geometric graphs. I mean, the case where the partition is the initial case would be like a tessellation, right? You would have classes and they would not overlap.
Mm-hmm.
And there are lots of problems in random geometric graphs where you would have some other objects than tessellations. There's, for instance, these SINR cells which do overlap. And so you might dream of a situation where when there is the noise could be like that you have could be like the fading. And so you might then, out of that, I suppose, have tools to identify. You may forget, I mean, the story of the geometry, but you might identify what are the communities would be the coverage cells. So it's more a question than a comment. So my point is that
if you know that?
Yeah, there are interesting objects that show up in, say, wireless stochastic geometry, where the communities would be the coverage cells. So then you would, if you would discretize space, you would have a link between 2 points of the Euclidean space if they are covered by the same base station.
Okay.
So this might be blurred by the noise, which would come from fading or shadowing or something like that. And then, I mean, out of the knowledge, the blurred knowledge of how points are covered, I mean, where they belong to, there is an edge between points if they are covered by the same base station, that would be the community 1. But you may be covered by another base station, you would also belong to community 2 because there is another possible overlap. And so I think these tools, I mean, I missed the introduction, but these tools might be interesting in this setting.
For this, yeah.
Because I mean, this is when the SNR threshold is more than, less than 1, then you may have high-level overlap. And I think people are interested in getting some ideas of these cells. I mean, so the detection of communities would then boil down to would be equivalent to identifying
overlapping
types of coverage.
Okay.
So it's just an analogy. So their geometry might play a role because here you have done geometry, right? So you identified your communities from a graph, but there is no geometry at all, right?
In fact, the only geometry comes from the fact that the matrix of eigenvector has some structure, and the structure is in fact that the row in the matrix U associated to a given node will be the sum of all the rows associated to the pure communities that are in this node.
Yeah, there is no Euclidean.
Yeah, but.
Okay, so thank you.
You mentioned the errors you get in is still quite big. And I just wondered if that's adequate for the applications you were talking about right at the start, where you're alluding to biological classification things. Do they break down if you've got errors as bad as that, like 25%?
I don't know. I didn't. No, I think it's. But I don't know if the networks are as sparse. I don't know the level of sparsity in protein-protein interaction networks. But I think they wouldn't be satisfied with 25% of error.
Yeah. So it's still some work to do.
Yes.
So thank you, Emilie.